This is Algebra 2 with Trig 7.6, Day 2. We'll be solving logarithmic equations. Logarithmic equation, it's an equation involving logarithms of variable expressions. What the of variable expressions means is that when you're doing the variable, or when you're doing the logarithm of a value, it's a logarithm base 6 of something. So the logarithms of a variable expression is implying that the variable is what the logarithm is calculating. Extraneous solutions are apparent solutions that have to be rejected because they do not fit into the original equation. So when we're calculating through and we come up with some x values that might equal a negative value, or any number, really, it could be positive, that when you plug back into the original problem, you're trying to take the logarithm of a negative number. You can't take the logarithm of a negative number. Any number raised to a specific power isn't going to change its sign, isn't going to get it to become negative. So the way we're going to work at these, we're going to take the logarithm base b of x. It equals a logarithm base b of y. As long as the bases are the same, we're going to look past the logs now, because it's equal, and we're going to look into our two expressions, our x and, in this case, the y, and we're going to set those equal to each other and try to solve. When we come down to the first one, we see log base 7 of 6x minus 16 equals log base 7 of x minus 1. We're going to zoom in essentially, and just look at the x, the 6x minus 16, and the x minus 1. By subtracting x to both sides and adding the 16, I can divide by 5 to figure out that x equals 3. And that when I plug my 3 in, I get a positive value here, and I get a positive value there. So 6 times 3 minus 16 is 18 minus 16, which is 2. And 3 minus 1 also equals 2, which shows that those are the same. The most important is that those are both positive, but of course they should be the same. Our equation setting them up has forced them to be the same. The next one, here we have ln. ln, remember, is used when we have a base of e. So our bases are the same. So we're going to look past that and look into what we're taking the logarithm of. We're going to subtract 2x. Add 13. We'll divide our 5 out. And x equals 6. We can check that answer. We're expecting that the 7 times 6 minus 13, which is 42 minus 13, which comes out to be 29. And the 2x, well, it's 2 times 6, plus 17. The 12 plus 17 makes 29. Those two values are positive, and they're the same, so that's a great check. What are we going to do with this third example? Notice how it's set up very similarly to the other ones. We have the same base, so we can look at what we're taking the logarithm of. We're going to solve this just like a typical algebra problem. Subtract the 12. and divide by the 4. So x is going to be -1. And we can check that by plugging the -1 into the 8. Now notice, we got an answer of -1 this time. So -2 plus 8. Well, let me check my work there again. I wasn't afraid of it being a -1 because when I added the 8, I still got a positive number. But I'm recognizing over here, I lost a sign. I'm sorry. 6x minus 12. This should be 6x minus 12. So I'm going to add the 12 to both sides, which is going to create a 20. And when I divide by 4, I actually get 5. So x is actually 5. You got to watch your sign. I blew that. So now I'm going to plug in my 5, which gives me 10. Now remember, the -1 wasn't ruled out just because it was a negative. When you plugged it in, you would have gotten a positive result. Now when I look at over here, it would have created negative. But the real answer is 5. So we plug the 5 in, we get 10 is 18. When we plug the 5 in, we get 30 minus 12, which is also 18. And those match, so it's equal. On the second side, we're going to be looking at a little bit different type problem. We're trying to solve for x. But notice we don't have a logarithm on both sides, so we can't just kind of zoom in and work with the 3x minus 8. So notice how this logarithm equals a number. So we know what the logarithm equals. So we don't really need the logarithm at all. If we know what it equals, then we're set with writing it as an exponential. So we're going to use exponential form. So that means to take the 5 raised to the second power equals 3x minus 8. So 5 squared equals 3x minus 8. That's 25. Add the 8 across. Divide by the 3. And x equals 11. We can check that when we plug in our 11, we get 3 times 11 minus 8, which is 33 minus 8, which is 25. That's a positive number. So most likely that's going to be fine. Now to understand how it would work up here, the 25, so this is log base 5 of 25. 5 to what power equals 25? It's saying that 5 to the second power equals 25, which would be true. Now the second one's a little tricky. It has 2 logarithms on the same side. We can't ignore those logs. Notice the base. The base doesn't have a number. That's called a common log. And that means base 10. So remember the properties when we learned about logarithms. If we're adding 2 logarithms together, we can write it as a single log and multiply what we're taking the logarithm of. Now we're going to use exponential form, because we know what the logarithm equals, and what it equals is a whole number. So 10 squared equals, we'll distribute that through to get 5x squared minus 5x. Now if you have an x squared and an x, an a value and a b value, then you need to get it equal to 0 on the other side. So we're going to subtract the 100 to the other side. 10 squared is 100. So this is a quadratic. So we'll factor out the 5. And then we can factor apart x minus 5, x positive 4. That multiplies to be negative 20 and adds to be negative 1. So now, does 5 equal 0? No. Does x minus 5 equal 0? When x is 5 it does. And does x plus 4 equal 0? Only when x is negative 4. So looking up at what would happen with a negative 4 would plug in to give us a negative 20. Well, we can't. 10 to no number gives us a negative 20. So that's our first example of an extraneous solution. When we plug in 5, we get a positive, and 5, we get a positive. So we're all set. So circle your answer. Lightly cross out the other answer. Don't erase it. Don't not write it. So this next problem, looking at it, a little bit easier than letter B. We're going to use exponential form because we have the logarithm equaling a value. So this is 4 to the 5th power equals 10x plus 624. So 4 to the 5th power, probably not one that you're real familiar with, but 1024. And then using algebra, notice how there's just one type of x, so I don't need to move everything to the same side. I need to subtract out the 624, divide by the 10, and I get a value of 4. Actually, I get a value of 40. So when I plug 40 back in, 10 times 40 is 400, plus 624 is 1024. 4 to the 5th power is 1024. So I know that that gives me a positive number. What do we see with this letter D? Some people get confused and it looks like this says x equals 2. It's not saying x equals 2. It's saying the log base 6 x minus 9 plus log base 6 of x. All of that equals 2. So it says plus in between two logarithms with the same base. So I'm going to write it with a single base. I'll put the x in front just so it really looks like what we're used to with needing to distribute, and that still equals 2. So now we're going to use exponential form. Which is going to be 6 squared equals x. That's x squared minus 9x. Now notice how this has two different types of x's. It has an a value and a b value. So I need to set this equal to 0 on one side and subtract over 6 squared, which is actually subtract over 36. 6 times 6 is 36. So I can factor that apart. And I know that 12 and 3, that multiplies to be 36. I need more negatives than I do positives, because it adds to be a negative. but it's got to be a negative 36, so multiply has to have a positive and a negative number. So I'll set my 12 minus, or x minus 12 equal to 0, 0 product property, and get negative 3. And when we plug the negative 3 in either spot, it would give us a 0. So we know that this gets crossed out. We call that extraneous solution. And we plug in a 12. The 12 gives us 12 minus 9 is 3, and just 12 gives you two positive values. So the 12 and 3 is 36, 6 to the second power is 36, so that makes sense. Okay, looking at letter E. Letter E is not any trickier. It does not have two logarithms, so we're going to go right to use exponential form, because we know what the logarithm equals. 3 cubed equals 2x plus 9. Well, that's 27. Subtract across the 9. Divide by the 2. And if we check that, we would get 2 times 9 plus 9, which is 18 plus 9, which is 27, which is positive. That's telling us it's good. But 27, 3 to the third power is 27. So I know that that's a great match. So we have a story problem. The population of deer in a forest preserve can be modeled by this equation, where t is the time in years from the present. How many years will the deer population, how long will it take for the deer population to reach 500? Well, we're starting out with our formula. And we know we want the population to be 500. So for us to continue to isolate t, or at least isolate the logarithm, I can't bring the 50 with the 200. This is 200 times something. So the best I can do is subtract the 50 to the other side. Now I can divide. So when I divide this out, I get 2.25. Now we look at this and we try to figure out what to do next. Because a logarithm equals a number, we can use exponential form. Now what base are we working with? Some people call that base 10 because no number is written, but natural log isn't base 10, it's base E. And when we use our calculator, we come up with 9.49. We'll subtract the 1 to see 8.49, which is about 8.5 years.